and gentlemen, I think we should start the next talk, which will be about our software Agros2D. It's a software for solution of physical fields, which is aimed to be used by engineers for solving the problems. The project was developed. Project was founded by Karban, who is the main developer and second head. And the list of other contributing people is on the screen. The software is using the Hermes library, which was founded by Shorin many years ago. And now it's developed mainly by Lukáš. He will speak about it tomorrow. So some of the features of the Hermes library are also available through our software. So I will not speak about them in detail because it will be done by Lukáš tomorrow. The development takes place the Department of the Theory of Electric Engineering in Pilsen, where these people work. So also Agros and Hermes are now developed side by side. Here's the content of our presentation. So in the introduction, I will speak about what is this software for, and I will present some key features, which will then be shown in those three examples. They are the main part of the presentation, and we will try to show that even quite complicated engineering problems, which include several fields which are coupled, or nonlinearities, or particle tracing, and more, can be done in our software in a very easy way. So let us proceed to. So before I start, I would like to welcome everyone to download our application. It is open source project, so everyone can download and use for free. Unfortunately, we were not able to finish the new version prior to FEMTEC. We're trying hard, but just didn't make it. So if you will download the stable version, it's like more than 1 year old. So it doesn't have all the features we will be speaking about, but we will try to upload it as fast as possible. You can also check out the Git repository where all the source codes are. So this is the basic characteristic of the application. As I said, the development started 4 years ago. It's a multi-platform application. It can be run on the Windows, Apple, and of course Linux, where it's also developed. We have feedback from several universities where it is used for education, but there are also some companies which use Agros for development of their products. We also use Agros for writing many papers. Another feature of our code is that we have many languages, and it's thanks to many people who translated to other languages like Bartek here, to Polish, and other. It's just a map of downloads around the world. So we have, we can see only downloads for the Windows version, and we had almost 7,000 last year, and there are probably many more people using it on Linux, but we don't know how many. Here is the list of physical fields that we are supporting. Our philosophy is that we completely separate the code itself, which is responsible for solving the partial differential equation, and the definition of the field itself. So for each of these fields, we created a XML file, which in some meta language describes the field, the types of boundary conditions, preprocessor, postprocessor, everything. The good thing about it is that everyone can design his own module if this is not enough, and he can do it without knowing how the implementation of our software is done. So he can just look at one of the XML files and design something similar, and then use it for his specific calculations. The Agros software is also focused on calculations in multi-physics, so we can couple some of these fields together, as you will see in the second part of the presentation. So here is the list of some main features of our code. As I said, some of them are actually features of Hermes library and are inherited in our code from there, so I will not speak about them. These are basically these. But on the other hand, Agros is not just a GUI to Hermes, so there are quite complicated structures that allow you to use Hermes efficiently. So it's like a definition of steady state, harmonic, and transient analysis, couplings, adaptive transient problems, and everything that is done in postprocessor, like evaluation of quantities, integrals, exports to some other programs, and also scripting support, which uses Python language. Another important thing is the material browser, where we have, well, for now not so many, but we want to have a complete library of material properties, many materials. Okay, here are the main features that are possible thanks to Hermes library, namely curvilinear elements, which allow us to discretize exactly areas like that, and also automatic HP adaptivity with arbitrary level hanging nodes. As I said, Lukáš will speak about it tomorrow. This is another important feature to Hermes, multi-mesh assembling. When we have several physical fields, the first thing is that usually they occupy different part of the space. So we need to have more meshes. So for example, for magnetic field, we have a mesh in the home domain, then we have a mesh for heat transfer in a part of the domain, and also this mesh can be denser or less dense depending on the properties of the field. So for example, if we need to resolve this field more precisely, we can refine just this mesh, which can save us degrees of freedom. the last picture is for structural mechanics, where we consider only this small domain. And here is example of solution of couple of problems on the meshes that I showed before. And so again, the magnetic field is in the whole domain, heat field is only in this part, and structural mechanics in the small part. This is just an example of adaptivity. This example is a spark gap. You can think about it as axial symmetry. So if you take this as an axis of symmetry and rotate the whole thing around the axis, you can imagine two electrodes here. One is a sphere, and the second is as a pointed shape. And there is a singularity here at the sharp edge. So we need to resolve it exactly, and that's done by the HP adaptivity here. Okay. So now for those who are not familiar with engineering code, I will describe shortly how the work is done. So the first thing is that we choose what field will be considered, and then we draw geometry and assign some material properties and boundary conditions. So this is what we call pre-processing. The second step is we have our geometry, but we need to have a mesh where we can calculate our problem using finite elements. Our code uses external mesh generators, but they are called automatically. So just by pushing one button, we obtain our mesh. Then the main part for the software is design, is the calculation, but the user is completely shielded from this. So it usually works, and what it produces is some visualization of the field variables, like temperature or magnetic field or whatever is being calculated. But for engineers, it's not usually the most important thing, because they need some other quantities which are derived from the field variables themselves. And not only quantities, but also integrals on surfaces or in volumes. All these, or many of these quantities are prepared in our modules. Of course, if it's not sufficient, everyone can add his own quantities using this concept that I mentioned. You can simply add them into our XML file. But all the basic, most common are already implemented, so there's no need to define them. Okay, there are more advanced features of the post-processor, like drawing charts, creating movies, images, and so on. Yes, and also, this is a new feature in this version, which is particle tracing. So when we calculate, say, electric and magnetic field, we can calculate the trajectories of particles with electric charge. And the last here is our scripting support. This is a very, very powerful tool, because you can use the results of your calculation in Agros together with Python and any Python library you have. So you can use NumPy, you can use SciPy, everything together with the results of the calculation. And of course, you can plot graphs and everything using Python. Okay, so that's for the introduction, and And now let us to proceed to the first example. It's the thermoelastic actuator. Here's the picture of the device that was built in our department, and there is the scheme of the device. This actuator is used for precise positioning of some sensors or something like that. And the basic principle is that you have a armature and a coil around it. We put the harmonic current into the coil, which produces a harmonic magnetic field, and it produces eddy currents in the armature. The eddy currents produce Joule losses, which heat up the material and it prolongs. So that's the basic idea. You can see that there are three physical fields in this problem. There is magnetic field, heat transfer, and elasticity. So we will step by step model all three of them. So first is the magnetic field. Harmonic magnetic field is described by this equation for the magnetic potential. Here are the eddy currents, which are produced in the armature, and Joule losses, which will be after that used as a source of the heat calculation. Okay, so let us first start from scratch and define the geometry and magnetic field. So we start with selecting the field we want to use, which is magnetic field. And we select basic properties. We want to use harmonic analysis. Okay, we select the frequency. Proceed to we use axisymmetric calculation. We start the definition of our geometry by selecting nodes. Then we change the mode and create edges which are connecting those nodes. Also use some notations, translations, and like that for creating more points one step. As I said, we support curvilinear elements, so we have this shape of the boundary. A good idea to save the problem in the case it fails. Now we are putting material markers, so each area has a different marker. We will use it for the definition of fields later. Now we have to define materials. So we have copper, which is used as an inductor. So we prescribe external density, external current density. Of course, it's harmonic field, so we have two of them here. real and imaginary component. Another material is the brass. Proceed to boundary conditions. For the magnetic field, we use just this simple condition, zero vector potential, which is both on the axis of symmetry and the fixture's outer boundary. So the boundaries are set, and now we assign materials to all the markers of the domain. Okay, so that's basically what we have to do for the magnetic calculation. Now we use the triangle to create a mesh. We can also adjust how dense a mesh should be in each area, and also we can make it refined towards some boundary. So we wanted a finer mesh inside the armature, which has been done now. Now we solved the problem, so far only in magnetic field. Now we can display flux density or other post-processing features. Also force lines. Then we can calculate volume integrals, which you can see many quantities there. You always select some part of the domain, and the values of the integral are in the right box. We of course can also inspect point values. All the derived values are again displayed there. Okay, I think that's for magnetic field. So we can proceed to the temperature field.
Just a quick question. I
Yeah.
don't know if I missed it. Did you guys explain how do you feed the PDE? How do you describe the actual equation?
The equation is shown here.
But how do you provide that model?
Well, that's in the XML file. So you can either use what is there are many options like harmonic field, transient analysis for magnetic, for heat.
So is it like a preloaded example?
It's not an example. It's just there is a finite set of problems that engineers usually solve, like in terms of physics, in terms of equations. All these equations are stored in some. The weak forms are stored here in the XML file. And like it's not really easy to read it, but it's there. The equations are there. If you want another, you can create some file like this.
So when you provide that XML file, which essentially has a string,
Yeah.
right, a text string, do you have some sort of parsing engine that goes through that string?
Exactly. But that's internal.
Yes,
I
of
mean,
course.
when you download your Windows installation, you don't care about that. Yeah, but we just write these files, and then we call some parser, which create C++ sources, which are then linked to our application.
And you have obviously, I'm going to stop here with a question, but really quick. That parser goes through the text and recognizes the differential terms.
Yes.
And where are they located? And do you have some sort of support for actual high or like operators, like say gradient? Like, Can you write like grad T plus K, so for example?
No, so far we just...
Just the differential terms, right?
Yes.
Second order as well?
Second order.
That's cool. Thank you.
Okay, so this is the equation for the temperature. It's dependent on time, so it's transient analysis. And the boundary, there is this type of boundary condition which describes convection. Okay. Let us return to the model. So we have to add another field, which will be the heat transfer, and again specify the basic settings like it's transient. Again, you can see the equation here, and then you have to put some initial condition. Okay, here is the coupling, which is automatically selected. If you add magnetic and heat field, then you have this coupling. You can also, of course, switch it off, but by default it's on. You have to define new material for the heat field. It's also brass, but now we specify the coefficients which are used for the heat calculation. Okay, and also another for copper. So this is density, and specific heat. Finally for silicon. And now the boundary conditions, convection, the outer boundary. This is the outside temperature. And we prescribe zero flux on the axis of symmetry. So that's it, zero flux. And on the outer boundary, prescribe convection. Assign again the materials and the domains. You can see different meshes. This is for magnetic field, where we calculate in the whole domain, and for the temperature field only in this part. It's the physics for the program. Now we started the calculation, which will take more time because first we have to calculate the magnetic field and then the transient analysis for the heat field. Here is the adaptive time step length, and which can be set here. This is the calculation with another setting of the transient analysis. We can view results in all time levels. We select the time step here. You can see what time we are looking at it. We can see that here the armature was heated by the jalousies, mostly here, but due to convection, it's can again view all the post-processor quantities. And we can also show a video in process. So the next step is the structure mechanics, which is described by Lamé equations, which are here with some coefficients. So I think we can proceed to the step. So far we have two fields, and we need one more. We need to add structure mechanics. Time it's going to be simpler because we need only one material, which is brass. Setting Young modules and Poisson number. Boundary conditions, which are of three types. We need fixed condition here because it's fixed there. Then we need fixed free conditions on the sides and the free condition on the top. So we have everything. We have three meshes, and now we can start the final calculation. So first we calculated magnetic field, and then we always calculate heat field and elasticity. Results, and this is the initial step where no movement is done, and here you can see how the armature moved through the whole process that I described. You can also make some 3D plots. Field and this is the flux density, the actuator itself, not showing it in air. Okay, so that's the first example. So just to conclude it, you see that you saw that we used 3 fields and 2 couplings, transient analysis, and everything was done quite fast. Second example is electromagnetic gun. It also uses 2 fields, but now they are not coupled. It's an electric field, which is generated here by the pair of by its cathode and anode, and then there is a magnetic field which is generated by this coil. Again, it's axial symmetry, so the picture should be rotated around this axis. The idea of the device is that for cathode there are emitted electrons which are accelerated by the electric field, and at the same time they are focused by the magnetic field to create an electron beam. So there are two fields, but no coupling this time. So we will show how the fields are calculated, and then we will show the particle tracing result. So the electric field is described by this simple equation. The epsilon is permittivity. Again, we can do it step by step. So first the electric field. Okay. So we will do it only once. So this is the electric field, and the magnetic field described again by the vector potential A. And then the particle tracing will be done. Lorentz force will be calculated from the field. It's given by this formula, and the equations for movement of the particles. The speeds are quite high, so we will use relativistic correction to mass. So now we will not draw the geometry again, because you had the idea from the previous example. We will just load it. So again, we have electric field, magnetic field with the selective properties. Here is the geometry, which could be drawn in 5 minutes. These areas which you saw on the picture. Now we can start the calculation. This is the mesh. The calculation itself. Here is the magnetic field. Electric field, sorry, and magnetic field is here. This is the vector potential. The flux density is here. So we can also display the arrows for the vectors. So now let us proceed to particle tracing. We have some values here which are filled in advance: mass of the electron, charge of the electron, and initial position. We apply. We have a picture of the beam of electrons, which is accelerated in that direction, focused by the magnetic field here. So that's the whole thing. We can do many more things in post-processing, which can give you the idea how the device works.
Is that OpenGL or what is the graphics?
Yeah.
Alternatively Mesa on open source platforms.
Okay, so I think it's this example. And the last example is Morse-True magnet. This is the classical magnet you can see here. We will calculate the magnetic field, and we will use post-processor to calculate the force of the magnet depending on the distance of the armature. We will use the calculation from the total energy of the field, which is obtained as an integral. Then the force is defined. Mechanics is a derivation of the energy. The new thing here is that we are using a nonlinear parameter for permeability, which is there is a very strong nonlinearity. So we will use Newton's solver. So here is the equation again. Here is the way to calculate the total energy by integrating the energy density. And here is the formula for the force. So now we are using different part of the application, which is the script. There is Agros running, and here is another window in which is written a Python script. So you can use every Python command, every extension of Python, and also some special objects which are designed to access our application. Okay, so just simply, this is the description of the magnetic field. All these things can be manually set in the graphical user interface. This is just equivalent. Here is the geometry. And here is the material. This is magnetic permeability, and here is the table which describes the nonlinearity. So dependence of permeability on the flux density. Okay, here are points, edges, labels, and here is the script which uses force cycle to move the armature. So we will calculate the total energy in, I think, 6 positions of the armature, and by taking differential, we will calculate the force on the armature. Okay, so this is the Python log window. This is the main Agros window. Now we run the script, which will create the geometry for us, and run the calculation.
What thickness do you assume? Because obviously you're doing X and Y, but Z is assumed to be what?
So it's a 2D code, so we assume 1 meter by So this is more time consuming because we have to perform 6 calculations, and in each calculation we are using the Newton method. So it takes some time. We are using some technique to fasten it up by reusing the Jacobian. Here is the final calculation, and you can see in a graph which is drawn, and that is the interface is the energy, and the second is the calculation of the force. So using this scripting, you can calculate, or you can use Agros for more complicated calculations. We also implemented some optimization algorithms and so on. Here's the calculation. Here's the nonlinear parameter for permeability. Okay. So the nonlinear dependence can be shown here in 3D. So you can see that this coefficient is not constant, it's dependent on the result. That's why Newton method had to be used. Okay, that's it. We switch to the presentation. So you saw what we have now. Here are some ideas what we would like to do in the future. Of course, improve our algorithms, especially nonlinear calculations, which sometimes work, sometimes work not as good as we would like to. So we will improve that. Also, we would like to use this nonlinear dependence of parameters on different fields, which we do not support now. We would also like to connect our code with MATLAB or Octave in a similar way that it's done with Python now, because some people prefer MATLAB or Octave. And also we would like to connect it with some kind of software like OpenModelica or Simulink, which allow us to use Agros calculation as a part of some more complicated calculation, like for example to use some electric design to control our input or things like that. So that's it. Thank you for your attention, and if anyone is interested, either in Agros or Hermes, and would like to use it or contribute in any way, he's very welcome to let us know. So thank you for your attention. Are there any questions?
I just want to congratulate you on doing a demo that didn't crash.
Can the user define another equation with different differential operators to solve this?
Yeah, he can design his own XML file. He has to learn our meta language, which is not really obvious, but it's not that hard. And then you can define everything, and you can just generate source files and then compile everything and use.
Just a question for Ubuntu 12.10. I failed to install it somewhere. Somewhere it failed. Maybe I'm a bit too fresh. Or
Well, that's probably for the discussion, but we tested it on Ubuntu 10. So you can send us feedback and we will.
I want to see show this to my engineers, you know.
Any other questions?
Is it open source?
Yes.
So I can go ahead and look for and get inspiration for the parser?
Sure, you can find it in GitHub. They show the address. But you can just type Agros2D GitHub.
Are you going to be around so I can pick your brain for a little while, probably
Sure.
tomorrow or something?
Sure. You would like to discuss it?
Yeah, because I'm doing a talk tomorrow, and as you can see, I have a strong need for such mechanism.
Okay, great.
Thank you.
Thank you very much.